Okay, hello. Hi, hello. Hello, Imad, Kiplafan, Subhan, Jafar, and everyone else who's watching. Sorry for the delay today. Are there any questions for me before I begin, or should we do this? I'm audible, I assume, and I'm visible as well. The screen is visible. Pen doesn't seem to be working, so let me just fix that. Okay, working now, and should be fine now. Okay. Email, sure, I will check the email. Okay. Is this the last chapter? So our syllabus has sort of gone in a different way than it was supposed to. This is not the last chapter. I was supposed to do some graph theory with you, and I outlined a couple of lectures before I outlined what I wanted to do, but that plan has also gone out of the window since I've slowed down a bit and I have covered less material in each of the classes. So I don't know. We will do as much as we can in 28 lectures. Yes, Kiblathan, you have one thing to ask. What's that? So Subhan, until then, I don't know. I'll try to do the pigeonhole principle with you, the inclusion-exclusion principle with you, and after that, let's see how much time we have to do other stuff. But these are the three things that I want to do. I want to do mathematical induction with you, which you'll do in this class, and then hopefully the pigeonhole principle and the inclusion-exclusion principle. We may not get any time to do graph theory, so I might remove that from the course. But the set chapter, shall I ask it right now? I guess you can ask it at the end if it's a query about sets. Okay. Perfect. So let's begin. Okay, so it's an interesting idea that we're about to do today. And the idea is that of mathematical induction, right? And this is actually a new proof technique. We've not done proofs for a while, and I don't know. Perhaps some of you don't like proofs that much, but anyway, here's one more way you can prove stuff. So this is an important proof strategy. So this is a proof strategy, and it works by because we have these. It works on statements of the kind that assert. So statements, it's a nice strategy for statements of the kind such that for all n Pn, that is a statement that is asserting something about all of these n's, where these n's are positive integers or these n are perhaps natural numbers, right? So statements of such kind, for example, let me write one statement here. For example, this is something that we've already done, we've already proven, we don't need to prove it anymore, but these are the kinds of statements that you can prove. So the sum of first n consecutive integers is n times n plus 1 upon 2, right? So this is a statement about the sum of the first n integers, and it states that that sum is equals to n times n plus 1 upon 2. Now this is something that we've already proven, we don't need to prove anymore, but I will use this as an example to demonstrate the proof by induction strategy. Another proof can be the sum of first k odd integers is k squared, right? So the sum of the first k odd integers is k squared. This is again a statement about all the positive integers, right? So for all positive integers, if you're taking the first k odd integers, the sum is going to be k squared. So this k actually is a positive integer. Similarly, this n is a positive integer, right? So statements of this form, where the domain of discourse is not the sum of, but just the positive integers or the natural numbers, these kind of proofs can be done by mathematical induction. So if no other proof strategy is working when you're doing these proofs, then you can use the strategy of proof by induction. Okay, so let me just outline firstly what the strategy looks like, how it works, why it works, and then go ahead and perhaps do a few examples. So let's talk about how. Okay, what is this? How does induction work? And of course, we're talking about mathematical induction. We're not talking about electromagnetic induction or anything of that sort. So the proof by induction works in two steps. The first step is, so step 1, we prove the base step. The first step is called the base step. And the step 2 is to prove the inductive step. And so the idea is that the base step is the step that you're proving. So for example, if I prove the statement, so prove that P1 is true, right? So for example, if I take the first one here, so the idea was that this statement was giving me a formula for all n times n plus 1 upon 2. For the first one, what I'll have to do is that I will have to prove that the formula, works for n equals 1. So that's really nice, because in the first step, all you need to do is show it for just one example, the first step that you have. Since it was for all positive integers, I'm just going to go with n equals to 1. That's my first number, right? The first integer that it's being asserted for. So that's nice. That's easy to do. We just need to check. So for example, in the formula n into n plus 1 upon 2, I just plug in 1 and check whether the formula works or not. So I know that the first integer is just 1. So when n equals to 1, my sum is just 1, right? The answer should be 1, because that's the only integer that I have. So the sum is going to be equals to 1. So this should be the sum. And if I'm asserting that this is a formula that works for all n, then at least it should work for n equals 1 as well. So if I plug in 1 over here, 1 times 1 plus 1 upon 2, which is 1 times 2 upon 2, that's equals to 1. So it works for 1, right? So the formula, I've proven the formula works. The formula works for n equals 1, right? So that's the base step. This was my base step. Okay. The next step is to prove the inductive step, and the inductive step is a bit interesting. The inductive step says the following. Inductive step. The inductive step says that assume P, K, That is, assume that the statement is true for some kth integer, right? That the statement, that is, in other words, the statement is true for the kth integer. So we're assuming this, and show that the truth of k, that if this is true, that if pk is true, then pk plus 1 is also true. So what am I proving here? The proof is actually, I'm proving this implication. I'm proving that pk implies pk plus 1, or rather pk is true implies pk plus 1 is true. This is the inductive step that I'm doing. And the importance of this inductive step is as follows. It's not proving that just pk plus 1 is true, it's proving that based on the truth of pk. And that's important because notice this. If you have proven for pk, let's assume that you've proven for some kth integer, then you have the proof, then you know for sure that pk plus 1 is true. For example, if we know that p5 is true, and I have proven the inductive step, so what I get is, based on the inductive step, so I know that p5 is true, and I know the inductive step is true, which is pk implies pk plus 1, which means p of 5 should also, now I should mention that this is for all k, right, because we're assuming that this is an arbitrary k, so this is being proven for an arbitrary k, so for all k. And so if I have this inductive step, that is that I've proven this step, and this I already know, then p5 would imply p6 as well. So I can conclude that if p5 is true and if the inductive step is true, therefore I have the truth of 6, that is p6 is true as well. Does that make sense a bit? Are there any confusion? Any confusion at this point of how this inductive step works? The inductive step, I haven't shown how to prove this. We're going to do an example to show you exactly how proofs like these work. But the idea is that once you prove this inductive step, you can take the truth for any integer and claim that the next one must also be true. That's the importance of the inductive step. No, k equals to 5 is not the base step. I'm just using it as an example. But it can be the base step as well. And I'm going to combine these two ideas together of the base step and of the inductive step to prove. Negatives, we're not dealing with negative numbers here. We're just talking about positive integers or natural numbers. Okay. Alright, so here's the idea. The idea is that once you combine these two things, so the first one is if you have the base step and if you have the inductive step, then both of these combined completes your proof. This is a sufficient proof. This is a proof for all n. And the reason is as follows. The base step gives you p of 1. The inductive step gives you pk implies pk plus 1, which means if I combine the base step and the inductive step, from p, the truth of n equals to 1, I can go to p of 2. because I have the inductive step, and inductive step holds for all k, right? So if I start from p1, if I set this to be 1, if I set this 1 to be k, then I have the truth for k plus 1 as well because of the inductive step. And of course there's no reason for me to stop here. I can go from p2 to p3, I can go from p3 to p4, I can go from p4 to p5. It guarantees me that once I have the starting point, I can continue my proof and it will go on. So this is a very powerful proving strategy, right? If you have the base step and if you have the inductive step, you have a proof for all n, because the base step gives you a starting point and the inductive step gives you a way to go from that starting point to the next point, right? It's not like a cases proof. In the cases proof, you have to do something like this. So for example, in a proof by cases, you have to do p1, p2, p3 and so on. You have to prove all of them separately. I don't need to do that all of them separately. I just need to do one case, which is the base step. So that's the only case that I need to do, and I need to do the inductive step, which allows me to go from here to here, then here to here and so on. In a proof by cases, you will have to do all of that again. I will prove the inductive step again. I will explain it again. So the idea is that the inductive step tells you, inductive step, you're not proving this, you're proving that if pk is true, you're proving a statement of a kind, if p then q. This is a statement that you're proving, that the truth of p implies the truth of q. For example, in this sum, as an example, the example that we were doing, that the sum of n consecutive integers is n into n plus 1 upon 2, and I don't know, let's assume, we all know that this formula is correct, but let's assume that we don't know that. The inductive step will ask me to do the following. The inductive step will ask me that if the formula holds for pk, show if it holds. We don't know that it holds, but if it holds for pk, show that it holds for pk plus 1, which means you can assume that it works for k. So I can say it works for k, which means I know that it works for k times k plus 1 upon 2. That if this is true, if you can assume this to be true, then show that this must imply that you can also use it for k plus 1. So for k plus 1, it will be, if I place k plus 1 here, that's k plus 1, n equals to k plus 1, then this term will be k plus 2 upon 2. So to prove the inductive step, I will have to go from here to here. I will have to prove this step, that the truth of k implies the truth of k plus 1, and I'll do that in a bit if I don't have any other questions. How it guarantees? The inductive step guarantees if you prove it. If you prove the inductive step, then you have a guarantee. Let me show you. Let's just do this example and see how this works, right? So here's the idea. Let's do an inductive step. For the first example. So I have that, let's assume the formula works for k, right? So if the formula works for k, all it is saying is that 1 plus 2 plus 3 plus ... k is equals to k into k plus 1 upon 2, right? Now I want to show that, let me do it with some other, so I want to show that it works for k plus 1 as well. And let's see how I can show that. So let's see what I can do. So the sum for the first k plus 1 terms will be as follows: 1 plus 2 plus 3 plus ... plus k plus k plus 1, right? So I have the first k plus 1 terms, right? And now I want to show that if this formula holds, then this formula should be similar as well. That is, I should get this formula. Okay. Alright, so I don't know what this sum is equals to, but notice something, that if I write this 1 plus 2 plus 3 plus, before the k plus 1 term, there is the k term. So I already have the first k terms plus k plus 1, right? So I can break this sum into two parts. This is the first part, this is the second part. So the sum of k plus 1 terms is equals to this. Now I have assumed, my inductive step allows me to assume that the formula works for the kth term. That means the sum of the first k terms is this. Well, if that's true, I can just replace this entire sum by k into k plus 1 upon 2, and the next term is of course just k plus 1. And now we just need to do a little bit of algebra. So let's do it. Take the LCM. The LCM should be 2. On the left hand side I have k. Let's just open this up. This should be k square plus k, plus this should be 2 times k. This should be 2 times, hold on, I can just, instead of doing that, let's just write this as k times k plus 1, plus, because we did not have a denominator here, so this is 2 times k plus 1. And now I can take k plus 1 common here, so k plus 1 times k plus 2 divided by 2. And this tells me this is the same formula, n times n plus 1 upon 2. If you assume your n to be, if I assume my n to be k plus 1, then n times n plus 1 upon 2 is simply k plus 1 times k plus 1 plus 1, which is 2, divided by 2. So what I've ended up doing is I've shown that the formula works for k plus 1, and that completes my inductive step. And the reason is that I have not shown it independently. I have assumed this truth. This was an important component. I needed that it should work. The formula should work for the first k terms, and if I'm guaranteed that, then from that point I go to the next step. So in other words, what this inductive step is saying, that if you can get me something like this, if you can get me to the kth integer, I can give you a way to the k plus 1 integer. So the inductive step is not proving it for all integers. All it's saying is that if in your list of integers somehow, if in your list of integers 1, 2, 3, if you can get to the k, this inductive step will get you from k to k plus 1. That's all it's able to do. This inductive step on its own is not proving it for all real numbers. All it's doing is saying that if you can somehow get it to k, it will get you to k plus 1. Okay, does that make it clear now? Okay, let's look at the question. Sir, how can you break 1 plus k into, I'm not breaking it, I'm trying to prove it so I'm trying to check at this point. So this I was assume that it works for k, and now showing the formula for first k plus 1 terms. So this was a different sum, this is a different sum now. Okay, does that make sense? These are not the same sums. The inductive step was telling me that this one is you can assume, and now just derive the k plus 1 sum for me. So we are just going for the next sum, trying to prove this. So this is something that we are trying to prove for the k plus 1 term. Yes, ma'am. Yes, it's based on an assumption. That's true. The inductive step is based on an assumption, and on its own it can do nothing. Let me clarify. So the base step just gives you P of 1, and on its own it can't do anything. The inductive step can just tell you that if you have for k, then you have k plus 1. So P of k will give you, you need an assumption to be true. Without that assumption, the inductive step can't do anything. So on their own, this is useless and this is useless, right? But when you combine both of these together, when you combine the base step and the inductive step, so if I have the integers, what this allows me, it gives me a starting point for my inductive step. So when I use my inductive step, I'm assuming that the truth holds for P of 1. So the inductive step at this point will look like P of 1 to P of 2. Now this is an assumption that I'm making, but to make sure that I can make this assumption, this base step was already proven. So this base step guaranteed me that this assumption that I'm making is true. So yes, the inductive step is based on assumption, but when you combine it with the base step, that assumption becomes true, and it allows you to go from P of 1 to P of 2. Do you see, Maham, when you combine it with the base step and then you add in the inductive step, then you can go from P1 to P2. Now at this point, the inductive step allowed you to go from P1 to P2. You can repeat the process, use the inductive step again, and go to P of 3. And at this point, this assumption that you're making is already been proven because you had the inductive step before. So do you see, when you combine these two strategies together, the base step allows you to implement the inductive step one time, and once you can implement the inductive step once, you can implement it as many times as you want, and you can keep making this chain and keep going forward. And you have the proof for all n. Any questions? Awesome. If you have any questions, please ask. This can be confusing, but I want the basis to be clear. Great. Okay, so let me just recap this proof. So first, so in this step I did the, where is it? Done. So this proof that I was doing, I've already done a proof by induction while I was doing this example for you. I did the base step that I showed that the formula works for n equals to 1, and over here I showed that the inductive step is valid, which means the formula sum of first n integers is equals to n times n plus 1 upon 2. I showed the base step, which was that it works for n equals 1, and I showed the inductive step that if it works for n equals to k, then it will work for n equals k plus 1. In the inductive step, you're proving that if you have this assumption, then you can prove it for the next one. And when you combine both of these together, then therefore it works for all n. Okay, and this would complete the proof. So this is another proof that the sum of the first n integers is n into n plus 1 upon 2. Yeah, I'm going to do that right now. Let's do another example. Okay, example number 2. the sum of first n odd integers. Let's see what that looks like. Let's first try to come up with a formula on our own. Let's try to do this. So the first, if I set n equals to 1, so this is n. When n equals to 1, the first n odd integers are just 1. So the sum is just equals to, or rather, so the sum is just equals to 1. If I have two odd integers, so 1 plus 3, the sum is 4. If I have three odd integers, 1 plus 3 plus 5, the sum is what? 9. If I have four odd integers, 1 plus 3 plus 5 plus 7, the sum is 16. So maybe we can already see a formula that the sum for the first n, for the first one it's just 1, for the second one it's 4, which is also 2 squared, the third one is 3 squared, the fourth one is 4 squared. And so perhaps I can conjecture that for n it will be n squared, right? So let's try. Maybe for 5, maybe it works. 1 plus 3 plus 5 plus 7 plus 9, it's 25. It works for 5 as well. And so let's try to prove this for n. So I have a conjecture. I am making a statement that the sum of first n odd integers. Okay, I think I've missed a question. So what if the formula works for P1 only? Then our assumption would be incorrect. Then we won't be able to prove Pk plus 1. Yes, Hadia, that's exactly correct. So Manahil, if the formula only works for P1, you won't be able to prove the inductive step. But if you're able to prove the inductive step, then you can go from P1 to P2 as well. Okay, Safa is asking a question. Does induction only work for sum of n integers, or it can also work when you have to find some formula like question 4? I don't remember what question 4 it is, but what question 4 is. But we will do it for a couple of other formulas as well, right? We will do it for some summations, we will do it for an inequality, we will do it for harmonic series, right? We'll do a couple of different proofs, but the idea is it works for statements that work on integers, that is proving something, that's stating something about integers. Okay, so the sum of first n odd integers, here's the statement: odd integers is n squared. Okay, let's try to prove this. How will I prove this? By induction. So let's do a proof by induction. I have two steps to make. The first step is the base step, and the base step I've already proven, because when I was doing the when I was trying to make this conjecture, I've already shown that it works for 1, right? So for n equals to 1, it works, because 1 square is just 1, so it works. I have the base step. What I need to do is I need to do the inductive step. And so the inductive step is that assume it works for k and show it works for k plus 1. Alright, so let's try to do that. Now let's say if I assume it works for k, so assume it works for k. What does that mean? It means that 1 plus 2 plus 3 plus the kth, what's the kth odd number? The kth odd number is not, sorry, there should be no 2 here, oops. So 1 plus 3 plus dot dot dot, what's the kth odd number? So if this is n equals to 1, this was for n equals to 1, this was for n equals to 2, you can perhaps see that the formula 2k you can write an odd number, the kth odd number, as 2k minus 1. And so let's see that this 2k minus 1 works. So when k equals to 1, 2k minus 1 is just 2 times 1 minus 1 equals 1. When k is equals to 2, then 2 times 2 minus 1 is 3. When k equals to 3, 2 times 3 minus 1 is equals to 5. So the kth odd number, this was the first odd number, this was the second odd number, this was the third odd number. So the kth odd number is going to be 2k minus 1, right? So my kth odd number can be written as 2k minus 1. And I'm assuming that the formula works. So the sum of all of these odd numbers should be k squared, because that's the assumption that I'm making, that's the statement that I want to prove, that the sum is going to be a perfect square of k. Alright, so this is my assumption, this is valid, this is something that we can assume to be true. And now I want to show that it works for k plus 1. Okay, which means let's now try to do 1 plus 3 plus 5 plus dot dot dot. I get to the kth odd number, which is 2k minus 1, and the next k plus 1 odd number will be something like this. So 2, instead of k, I will have k plus 1 minus 1, which is 2k plus 2 minus 1, which is 2k plus 1. So instead of writing 2 times k plus 1 minus 1, I can just write 2 times k plus 1. So up until this point, I have k odd numbers, and this is my k plus 1 odd number. Is that clear so far? I'm trying to make a formula for the k plus 1 odd integers and their sum, right? So far so good. Okay, and since now I can use the inductive step, so I know that it works in my inductive step. I know that the formula works for k, so I can write this. I have assumed that for these I can just replace it by k square, because the formula works for the first k odd numbers, right? Now I want to find the next, so the next one is 2k plus 1, right? But this k square plus 2k plus 1 is nothing but, I can write this as k square plus 2 times k times 1 plus 1 squared. If you notice, this is a square plus 2ab plus b squared, which means it's nothing but k plus 1 whole squared. A squared plus 2ab plus b squared. So that's a plus b whole squared. And I have k plus 1 square. What is this? I've just shown that the sum is a perfect square of the k plus 1. So this is telling me the formula works for k plus 1, and that completes my inductive step. It completes the inductive step, which means that I assumed it works for k, and I showed that it works for k plus 1 as well. So now that I have the base step, since I have the base step n equals to 1, so for n, let's put this together. I don't need to write this, of course at this point your proof is done, but I'm just going to illustrate what happened. So base step gave me n equals 1, the sum was 1 squared, so the sum was 1 squared. The inductive step told me that if it works for n equals to 1, it should work for n equals to 2. The sum should be 2 squared. If it works for n equals to 2, it should work for n equals to 3. The sum should be 3 squared. If it works for n equals to 3, then it works for n equals to 4. The sum is 4 squared. And oops, let's not make it look like 42. and so it works, and therefore I have it for all n numbers. Therefore the sum of first n odd integers is n squared, and I've proven that. Okay. At this point, when you complete the basis step and you complete the inductive step, your proof was already done. All right. Any questions? Okay. Let's change gears a bit. Let's try to do another example. So show that another example. Show that the inequality n is less than 2 to the power n holds for all positive integers, for all positive integers n. Okay, so I have to prove this. Let's try to prove this. Again, we are saying that this is an inequality that holds for positive numbers. Jafar, yes, I showed the base step again just for your understanding. I had already proven the base step. We didn't need to do that. At this point, your proof is done, like I said. Okay, so let's prove this by induction. Proof by induction. Let's try the base step. So the base step should be n equals to 1. So n equals to 1. That means 2 to the n is just 2. And so the inequality n is less than 2n, 1 is less than 2 is of course valid for n equals to 1. So the base step is fine because you just had to check whether the inequality is true for n equals to 1. Second is the inductive step. The inductive step says that assume it works for k, that is k is less than 2 to the power k, and now it show that it will work for k plus 1, right? Now before I start to prove this, what will it mean to show that it works for k plus 1? If it works for k plus 1, then I can just replace this k and this k by k plus 1. So I have to show that if I replace this k with k plus 1 and I replace this k with k plus 1, then I have to show that k plus 1 should be less than 2 to the power k plus 1. Okay, I have to show this. I haven't shown it yet, but I have to show this, right? And I have to do this using this inequality. K is less than 2k. So let's show it. So here's the proof. Proof for k plus 1. We already know. We know that k is less than 2 to the k because we have assumed this in our inductive step. And now let's add 1 on both sides. If I add 1 on both sides, I get k plus 1 k plus 1 is less than 2 to the power k plus 1. My proof is of course not done yet because this is different from what I had to show. I had to show k plus 1 is less than 2 to the power k plus 1. But so far I have only shown that k plus 1 is less than 2 to the power k plus 1. At this point I can use that one, use the fact that 1, let's see, okay, yeah, I can use the fact that 1 is going to be less than 2 to the power k. And this is something that we already know, right? That if I have k equals to 1, then this is just 2. If I have k equals to 2, this is 4. So this 2 to the k is an increasing, this is an exponential function. Then of course, 2 to the power k is always going to be bigger than 1, right? So this is k equals 1. So I already know that 1 is less than 2 to the power k. So in this inequality, I have k plus 1 less than 2 to the k plus 1, but I know that this 1 is smaller than 2 to the power k, which means I can make another inequality here. I can say that this 2k plus 1 is going to be smaller than 2k plus 2 to the power k, right? And now I have, what do I have over here? I can ignore this middle inequality and just take the left hand side and the right hand side. I have k plus 1 less than 2 to the power k plus 2 to the power k. And this is nothing, so this is nothing but k plus 1 is less than, this is x plus x, so x plus x is just 2 times x, so that's 2 times 2 to the power k, and that's of course k plus 1 less than 2 times 2 to the power k is just 2 to the power 1 plus k, which is k plus 1 is less than 2 to the power k plus 1. And now this completes my inductive step because I've shown what I needed to show. I needed to show that k plus 1 should be less than, sorry, this is something that I needed to show. This was what needed to be shown, was this statement that I had written here. This is something that had to be shown, and I have finally shown this, that k plus 1 is less than 2 to the power k plus 1. That's my last statement over here, that k plus 1 is less than 2 to the power k plus 1, which means this completes my inductive step. So any questions? Should be 2 to the power k plus 1, yeah. It should be 2 to the power k plus 1, and I have finally shown that. At this point it was just 2 to the power k plus 1, but that wasn't the proof that I needed. Any questions? Awesome. That's great. So should we end this or should we do another example? So you understand the basics, right? You have to show a base step, you have to, oh, I should also mention something important. Let's suppose I have to do this. Okay, here's another statement. Show that, just a quick question to test your understanding. Show that, let's see, 2 to the power n, 2 to the power n is less than n factorial for all n, for all positive integers, n greater than equals to 4. What does this show? How will you prove this? Because this one doesn't start from n equals to 1, this one starts from n equals to 4. So this statement is not going to be true. You can check this. For n equals to 1, this is not true. 2 to the power 1 is not less than 1 factorial. 2 is not less than 1. So this, it's not true for n equals to 1, it's not true for n equals to 2, it's not true for n equals to 3. So what will be different in this proof? Let's see. And yeah, exactly, the base step in this proof, the base step has to be n equals to 4. So you prove it for n equals to 4 and then you do the inductive step. So n equals to 4, let's check that out. 2 to the power 4 is less than 4 factorial or not. 2 to the power 4 is 16, which is less than 4 times 6, which is 24. So it works for n equals to 4. And now you just fill in the details for the inductive step. I'm leaving this for you. It's also an example just from the book, but you can try to do it on your own and then do it. The example 7 is quite important. Example 7, by the way. This is something that I mentioned. Example 7 of the book. This is something that I mentioned when we were doing sequences in series back when we were, those ancient times when we were in the classroom. Example 7, I talked about the harmonic series, which was summation k equals to 1 to infinity of 1 upon n. And I said that this series diverges. And we didn't do the proof in class. I said we'll do it at some point. This proof that this series diverges can be done by induction. So example 7 shows that the harmonic series diverges, and this is a proof by induction. That's not the only way to prove this, but it's one of the ways. Okay. Alright, Subhan, base step would be 4. Yeah, exactly. Yes, the time has come to do it, and you can go through that proof on your own. I'm not going through that. If you don't understand it, then you can let me know and we can go talk about it. And that ends the formal lecture for today. If you have any questions, you may ask. Kiblathan, I believe, had a question related to assignments, but the sets chapter. You can ask that now. If applicable, can we use this proof strategy in your assignment? Sure, Ritika, go for it. Question 146, left, can't find. You'll share this note? Of course, I'll share this notes, Taha. I place all of the notes in the Google Drive folder. If a set is uncountable, then is there any way to prove that its subset is countable infinite? There should be a way, because that's something that you have to prove, right? You have to construct, I believe the question that you're asking is that you have to prove that an infinite set has a countably finite subset, countably infinite subset. मैं फिजूल में नोट सुना रहा हूँ. That's up to you, या फिर I don't know. I've posted on Piazza several times that these notes are available on the drive. Not infinite, because infinite means countably infinite and uncountably infinite. Yes. Infinite means infinite. Infinite means countably infinite and uncountable infinite. Yeah. Both of those. A set can't be uncountable and finite. If a set is uncountable, then it has to be uncountably infinite. So let me just clarify what the question is. The question says that if it is infinite, then it has a countably infinite subset, right? That's the question. You have to show that if it's infinite, then it has a countably infinite subset. Now infinite में दो cases आते हैं. First case is it's countably infinite, and then you show that it has a countably infinite subset. And the second case is that it's uncountably infinite, and then you prove कि अगर uncountably infinite है तब भी उसका कोई एक countably infinite subset होगा, right? So you just prove this. I'm assuming this is the question that you're stuck in. This is the proof that you're stuck in. And if you have an uncountably infinite subset, uncountably infinite set, how do you create a countably infinite subset out of it? I'm just confused whether it does exist, I believe. Please verify my question 12 solution. What's your question 12? Didn't I reply to all your emails, Jafar? I'll check it out and see if I haven't replied to any of your emails. Don't worry about it. Okay, I'll check it out. Anything else? Okay. All right, have a good day. I will just remove this from the notes before I post them. So, yeah. Okay. All right, have a good day, everyone. Bye.